In the last session, I have talked about the bulging or depression behavior based on solidification characteristics for the different range of chemistry for the plain carbon and low alloy steels, and also for the stainless steels. So, what I had mentioned there was for the different carbon concentrations or carbon equivalent concentrations, what will be the solidification mode, what is the solid shell, whether it is thick, what is the strength, what is the mushy zone. If the solid shell is thick, mushy zone will be narrow. If the solid shell is thin, mushy zone will be quite wide, deep. So, and where the delta to gamma transformation is taking place, whether near solidus, because near solidus is a real point of worry, because that is that temperature region where it is brittle. So, there is a possibility of crack formation, and what is the behavior of sticking or bulging based on this. So, there I had mentioned that for very low carbon and very high carbon, that means except for the peritectic chemistry range of 0.1% carbon, I am talking the temperature the chemistry range, it is not exactly 0.1, it may be 0.07 to 0.17. So, this particular chemistry range we have a depression tendency, I have told you why, and for lower carbon range compared to that and higher carbon range compared to that, we have sticking and bulging tendency. Similarly, for stainless steel, I have explained in the last session for 304, which has a nickel equivalent of chromium equivalent around 0.55, slightly more than 0.55. We have a high depression tendency. Why? Because this delta to gamma is taking place towards the end of the solidus. Delta to gamma around solidus is relatively high. Because of this, the depression tendency is relatively high, because it is taking place in the brittle temperature region. So, chances of depression will be more, the surface will be rough. But for other chemistry, there is other stainless steel grades which have either very low nickel equivalent by chromium equivalent, that means for the ferritic grades, or the totally austenitic grades where solidification is entirely through austenitic mode. What is happening is we have sticking or bulging tendency, of course for different reason. For very high nickel equivalent by chromium equivalent, similar to the behavior of very high carbon, more than 0.5% carbon equivalent, solidification is entirely through gamma, microsegregation is very high, the shell thickness during solidification is quite narrow, very thin, and the mushy zone is quite deep, it's thick. So, because of that, the sticking and bulging tendency is quite high, because the thin shell, solid shell cannot withstand ferrostatic pressure. But for the other extreme chemistry region, that means when nickel equivalent and chromium equivalent is very low, is like very low carbon for the carbon grades, for 430 say, ASI 430, nickel equivalent by chromium is very low. So, solidification is entirely through delta, the delta to gamma takes place at quite low temperature compared to solidification completion. So, the solid shell is, though it is thick, because microsegregation is less, but it is weak. Weak means, why it is weak? It has low strength. Why? Because it is delta. Not only during solidification, even after solidification completion also it continues to be delta for quite some time, for quite some temperature. So, this weak solid shell again may cause sticking and below the mold bulging. So, these are the tendency for different chemistry ranges. Now, the same behavior can be shown pictorially based on the distribution or carbon equivalent. So, first I will show to you what is the influence of carbon on sticking or depression behavior. I have told you, I have given you certain examples of different carbon contents, grades for having different carbon or carbon equivalents. Now, let us see for different carbon equivalent how the two strains are varying. I have told you that there are two opposing strains. One is the bulging strain or the streaking strain, another is the contraction strain. So, I have told you around 0.1% carbon, what is happening? This bulging strain is relatively less, and the contraction or depression strain is relatively high. Why this is relatively high? Why contraction and depression is taking? Because of the delta to gamma transformation taking place towards the end of solidification near the solidus temperature. That is why this is relatively high compared to other carbon equivalents. And incidentally, in this particular composition, this particular chemistry, the contraction strain is relatively high, but the bulging strain is relatively low. Why this is relatively low? Because you have a thick shell, and also towards the end of the solidification delta to gamma transformation is taking place. So, it has become already austenite. So, the shell is thick and strong. So, it can withstand ferrostatic pressure. So, the tendency will be more of contraction and depression rather than streaking or bulging. So, at 0.1 this is contraction or depression is predominating, and for high carbon equivalents around 0.25 and above, the streaking and bulging strains are relatively more. Why? Because of microsegregation, because of austenitic solidification predominating and increasing relatively, we have very thin shell. Because of that, it cannot withstand the ferrostatic pressure, ferrostatic strain. So, the streaking and bulging strain is relatively more compared to the contraction strain. So, therefore, the streaking and bulging behavior will predominate at relatively high carbon. Same thing is happening for very low carbon. You see, it is increasing and the contraction and depression strain is decreasing. So, both at very low carbon, that means say around 0.02, 0.03, 0.04, it is relatively streaking and bulging strain is more, and around say above 0.2, it is relatively more streaking and bulging. The reason may be different. Here the reason is very thin shell, here the reason is very weak shell. Solid shell is weak here because it is totally delta. Here it is totally austenitic. So, the shell is strong, but because of high microsegregation it is thin, and because the strain, streaking strain or the bulging strain is inversely proportional to the square of the thickness of the shell. So, that the thickness of the shell is narrow, it is thin, then it cannot withstand the ferrostatic pressure. So, the streaking and bulging strain is relatively high. Similar behavior you will see for stainless steel. So, there it was for plain carbon and carbon equivalent, it was the carbon or the carbon equivalent which is the deciding factor for chemistry. For stainless steel, as I have told you earlier, it is the nickel equivalent by chromium equivalent, the ratio of that, which is going to play a crucial role, which indicates how the chemistry is varying, how the solidification mode will change, and consequently what will be the solidification characteristics, what will be the bulging tendency or depression tendency. So, let us see here what is happening. You see, at around 0.55 nickel equivalent by chromium equivalent, similar to the situation of 0.1 carbon equivalent, here it is 0.55 nickel equivalent by chromium equivalent. The depression strain, the contraction strain, this one, contraction strain, this dotted, these points, circles, is relatively high. Why it is high? Because this delta to gamma transformation is taking place mostly in the crucial brittle temperature zone of 0.9 to 1, and because of that a lot of strain is generated, and because of that lot of contraction strain is generated, and because of that there is a depression tendency. But for very low nickel equivalent by chromium equivalent, or for very high nickel equivalent by chromium equivalent, this bulging strain is really much more compared to the contraction strain. For very low nickel equivalent and chromium equivalent, delta ferrite mode of certification is predominating, and delta ferrite is stable at quite lower temperature even after certification is complete. So, this weak delta ferrite shell, solid shell, is the cause of high bulging strain. Because it is soft, it cannot withstand the ferrostatic strain, so it is ferrostatic force, so it is relatively high, and the contraction strain is quite low. At high nickel equivalent by chromium equivalent, what is happening is it is austenitic solidification. Because of austenitic solidification, micro segregation is quite high. Because of that, solid shell is thin, and because of that it cannot withstand ferrostatic pressure or force. So, here also the contraction, or the rather the bulging strain is relatively high, contraction strain is low. So, the behavior here also is bulging. So, only at nickel equivalent, chromium equivalent of around 0.55 we have depression tendency, very predominant depression tendency, this region of the chemistry. Incidentally, 304, the common stainless steel, belongs to this chemistry range, nickel equivalent versus chromium equivalent around 0.56, 0.57. So, this is the chemistry where we have lot of depression, surface depression. And if you have surface depression, rough surface, because of that the heat transfer is affected and near the surface, and we have coarse dendrites on the near the surface, unlike other grades where we have relatively finer grain size at the surface because the heat transfer is quite high. Here this depression formation is creating air gap between the surface of the solid shell and the mold, and that affects the heat transfer, and that is why we have a lot of this, wherever there is depression, beyond the depression, lower beyond, not beneath the depression, we have coarse grains, coarse dendrites, which is again not desirable. The crack formation again becomes easier if you have a coarse grain structure. So, we have to keep in mind that because of nickel equivalent by chromium equivalent, at what nickel equivalent chromium equivalent there is a depression tendency, and at what chemistry we have bulging tendency. So, if you understand this, then accordingly we can select the casting parameters. We know the solidifying behavior, we know the intrinsic characteristic for the different chemistry. So, accordingly we can decide what should be the heat transfer in the mold, what will be the intensity of secondary cooling, because if there is bulging, that means you have to use relatively higher intensity of secondary cooling, so that the shell becomes relatively thick, more thick, and the temperature of the shell, as you are using more water, means temperature of the shell will come down relatively faster. So, the strength of the shell also will increase, and delta to gamma transformation will be enhanced. So, if you have austenite, the strength will be relatively more. So, to increase the strength of the shell, more amount of cooling is necessary, secondary cooling. So, depending on the solidifying characteristic of a particular alloy, we can decide what should be the casting parameters. We can decide how the different powder will be used. Powder means the mold powder will be used, because that mold powder, after it gets molten, so that is, it decides the thickness of the relative thickness of the solid vis-a-vis the liquid, region of the mold slag, between, I have mentioned these earlier, between the mold surface and the solid shell surface. What is the relative thickness of the mold slag, solid slag and the liquid slag? That determines what is the heat transfer characteristics. That determines how it can resist, sticking. So for sticking you have one type of powder, because the sticking has to be resisted. But for depression you have other type of powder where the heat transfer has to be relatively taken care of, because you have less heat transfer. So heat transfer should not be high in that region. So these are all dependent things. Depending on the characteristic of the particular alloy, you design your casting parameters. This is very important.